Hey guys, this is Sachin here, and this video is about mathematics behind computer graphics. Computer graphics involves a wide range of mathematical concepts and techniques, from basic arithmetic to advanced topics in linear algebra, calculus, and differential equations. So we are going to see some of the major topics which is involved in the computer graphics process. And I'm going to list out the mathematical ideas and concepts, and we are going to see it one by one how it is used in computer graphics. So the first one is basic arithmetic and geometry, linear algebra, calculus, trigonometry, affine and projective geometry, differential geometry, numerical methods, Fourier analysis, optimization techniques, graph theory, partial differential equations, computational geometry, probability and statistics, and some of the advanced topics like quaternion algebra, wavelets, differential forms, and etc. Arithmetic and geometry are foundational to computer graphics, providing the tools and methods necessary for creating, manipulating, and displaying graphical objects. Let's see the ways in which these concepts are used in computer graphics. So the first one is coordinate system and representations, vector operations, basic geometry, coordinate geometry, rasterization, collision detection, rendering and lighting, animation. Coordinate systems and representations. Points and coordinates. In computer graphics, objects are represented as collections of points in the coordinate systems. For example, in a 2D space, a point can be represented by pair of numbers x, y, while in 3D space it is represented by three numbers x, y, z. Coordinate transformations. Arithmetic operations such as addition, subtraction, and scaling are used to manipulate points and objects within these coordinate systems. For instance, translating an object involves adding a vector to each of its points, effectively moving it to new position. Second, vector addition and subtractions, or on overview, it is an vector operations. Vectors are used to represent directions and magnitude in space. Adding or subtracting vectors helps in calculating the position of objects, determining directions, or moving objects within the scene. Dot product. The dot product is a fundamental operation used to determine the angle between two vectors, which is crucial for tasks like lighting calculations, example determining how light interacts with the surface. Cross product. The cross product of two vectors is used to find a vector perpendicular to both, which is essential for calculating normals to surfaces. Normals are used in shading to determine how light reflects off a surface. Basic geometry, shapes and polygons. Basic geometric shapes like triangles, rectangles, and circles are the building blocks of more complex objects in computer graphics. For example, 3D models are often composed of mesh of triangles. Distances and angles. Calculating the distance between points using distance formula and angles between lines using trigonometric functions is crucial for positioning objects, detecting collisions, and rendering scenes. Geometric transformations. Geometry is used to describe transformations such as translation, rotation, and scaling. These transformations involve simple arithmetic and matrix operations, allowing objects to be moved, rotated, and or resized within the scene. Coordinate geometry, line equations. The equation of a line in 2D or 3D space is fundamental in graphics for rendering line segments, drawing shapes, and computing intersections. Intersection testing. Geometry is used to calculate intersections between geometric entities like lines, planes, and polygons. This is crucial in rendering techniques such as ray tracing, where rays of light need to intersect with objects in a scene. Bezier curves are splines. These are used to create smooth curves and surfaces in graphics. They rely on arithmetic operations to interpolate between control points which define the shape of the curve or surface. Rasterization. Pixel operations. Arithmetic is used in the process of rasterization where vector graphics described by points, lines, and shapes are converted into raster images, which is a grid of pixels. Calculating which pixels should be colored to represent a line or a shape on the screen involves geometric algorithms. Line drawing algorithms. Algorithms like Bresham's line algorithm use a basic arithmetic to determine which pixels should be illuminated to represent a line between 2 points on a screen. Collision detection. Bounding boxes. Simple geometric shapes like rectangles or circles in 2D and boxes or spheres in 3D are often used to create bounding volumes around objects. Collision detections involves checking whether these bounding volumes overlap, which requires geometric calculations based on object positions and dimensions. Hit testing. When a user clicks on a screen, arithmetic and geometry are used to determine if the click occurred within a certain object, which is essential for interactivity in graphics applications. Rendering and lighting, ray surface intersections. In ray tracing, determining where a ray intersects a surface involves solving geometric equations. Lighting models. Geometry and arithmetic are used to calculate how light interacts with surfaces, including diffuse and specular reflections. These calculations depend on the angles between the light source, surface normal, and the viewer's direction. Animation, motion and transformation. Geometry and arithmetic are used to compute the movement of objects over time. For example, interpolating positions for smooth transitions, linear interpolation, or more complex spline interpolation is common in animations. In summary, arithmetic and geometry provide the essential tools for defining, manipulating, and rendering graphical objects. They allow us to describe how objects are positioned, how they interact with each other, and how they transformed and displayed on a screen. These concepts form the backbone of more complex operations in the computer graphics.